So welcome back to part 2 of lecture 20. In the first part, we proved that we have this kind of ascending chain of subspaces. So the subspaces get kind of larger and larger and larger as we take higher and higher powers of t and look at their null space. And the second lemma, we showed that if at some point on this chain that it stabilizes, like when you go from one subspace to the next, you get equality, then it stays stable from then on. So the question is like, does this ever happen? Does it stabilize? And the next lemma actually shows that the chain will stabilize at least by the dimension of v's power. So the dimension of v is like 7. When you get to the 7th power, it will have stabilized. It may have stabilized a little bit earlier, but you know for sure by the time you get to the dimension, the chain will stabilize. It will not grow anymore. So as the lemma here, I'll state it as the null space of the operator t raised to the power dimension of v is the same thing as the null space of t to the l for any l bigger than or equal to the dimension of v. And here's how we're going to do it. Really all we need to do is show that we have equality here. If we can show that the dimension of the null space of t raised to the dimension of v is equal to the dimension of the null, not the dimension, sorry, this space here is equal to this space right here, then the previous lemma then says then it will always be stable. Okay, so what we're going to do is do a proof by contradiction. Suppose that it doesn't stabilize, that when you go from the null space of t raised to the dimension of v, you actually get something still strictly smaller than the dimension of t raised to the dimension of t raised to the dimension of v plus 1. So what that means is that at no point when you looked at this chain did you see any equality from going from one subspace to the next. It gets bigger and bigger and bigger at each stage. Okay, but let's look at what this means in terms of dimension. Right? So what you have is that 0 must be less than the dimension of the null space of t, and then because it's strictly bigger, then the dimension has to go up, right? So the dimension of null t squared, and it keeps going all the way up to the dimension of the null space of t raised to the dimension of v plus 1. Okay, and so when you look at this, what this forces is that this dimension has to be at least 1. This dimension has to be at least 2. This dimension has to be at least 3, and so on. Right? So this forces the dimension of n to the null space of t to the I to be greater than or equal to I. Okay, but this means that the dimension of this last subspace, I'm missing an L here, I'll fill that in, the dimension of this last subspace is greater than or equal to n plus 1, right? But this can't happen. But the null space of the operator of t raised to the dimension of raised to the power of dimension of v plus 1 is a subspace of v, right? So we also know that the dimension of the null space of t raised to the power of dimension of v plus 1 is less than or equal to n. So we have these two statements. We have this inequality and this inequality, and you can't have both of them true at the same time. Right? So we have a contradiction. So this is a contradiction. So we have that the null space of t raised to the power of the dimension of v is equal to the null space of t raised to the dimension of v plus 1. And to finish off the proof, you now apply the previous lemma. And I think that was lemma 2. And that finishes off the proof. Okay, so this is great. Right? Because now we have kind of a bunch of subspaces that get bigger and bigger and bigger, but at some point it will stabilize. And the thing that we can prove of this is kind of the following theorem, is if we know that the dimension of v is n, then v can be written as this direct sum. It's the direct sum of the null space of t to the n plus the range of t to the n for any operator, right? And there's nothing special about whether you're using the real numbers or the complex numbers. This will always be true. So it gives us a way of breaking up any vector space using our operator. So let's say let's prove this. And because we're just trying to show that V is the direct sum of two subspaces, all we need to do is show that the only element in common between these, this should be an intersection. The only thing that we need to do is show that if there's a vector in the intersection, it has to be the zero vector. Okay, so let's prove this. Well, because V is in the null space, we know that t to the n V is equal to 0. And at the same time, we know that V is in the range of t to the n. So that means that V can be written as t to the n to evaluated at W. There's some W that I can plug in Tn and then I get V. Okay, so this is what I'm given. And now what we have is, so T evaluated at T raised to the power of t to the n evaluated at W is the same thing as T raised to the power of n evaluated at T n W. Okay, so that's just kind of breaking up the powers here of the operator. T to the n evaluated at W is V. Right, that comes from the previous line. And T raised to the power of n evaluated at V is 0. Okay, so what do we get from this, right? Well, what we have is, since the null space of t to the n is equal to the null space of t to the 2n, right? So that's just, this comes from all the work that we did before, from all the other lemmas. And since W is in the null space of t raised to the power of 2n, that's what we just showed right here, we have that W is also in the null space of t to the n. Okay, and so W is in the null space of t to the n, so this fact right here means, hence V, which is equal to t to the n evaluated at W, but W is in the null space, is 0. Right, so V is equal to 0. The only element in the intersection is 0. So we got part of the proof here. So just to kind of recap here is that hence we have that this is a direct sum. Okay, this is a direct sum because the only vector in common between these two spaces is the 0 element. But now we have to show that this direct sum is all of V. And then we're going to use a dimension argument to prove this. So since the dimension of V is equal to the dimension of the null space of t to the n plus the dimension of range t to the n, this is just the fundamental theorem of linear maps, and this is equal to the dimension of the direct sum of these two spaces. So what we have is that V and this space right here have the same dimension. So, right, so here I'll put, since we have a direct sum, so just by a dimension argument, this vector space and this vector space have the same dimension, so they actually have to be the same space. So we have that V is equal to the null space of t to the n direct sum range t to the n, which is what we wanted to prove. Okay, so that's kind of a nice result that we get out of our discussion of t to the n. What it's showing is that our vector space can be written as a direct sum looking at the nth power of our operator. Okay, so we'll put that aside for a minute, and when we come back, we're going to talk about generalized eigenvectors.